A very warm welcome, everyone, to our Cosmos Seminar series. Today, Luca Guzzardi will give a talk on multi-messenger astrophysics and epistemic reasons for cooperative behavior. Thank you very much, Luca, for being with you, and I leave it to you.
Thank you. Thank you, Sylvia, for the invitation. And I I must start apologizing because I was not aware. I then I discovered that last year, or 1.5 year ago, I gave a talk with the same title at the Max Planck Institute for the History of Science, but this is not the same talk. The reason is that already last year I was working on a paper uh, that has the same title, and but I mean, last year I presented some ongoing ideas, and this year is more this now it's more about results of this research. Uh, I also must say that there is a big picture in which my research is included, so to speak, that I call it's like a title of a research program, Varieties of the Scientific Ourselves. And the big picture is the emergence of the awareness that science is made by multiple subjects, both over time through history and space through mostly contemporary collaborations. What I'm trying to do is just try to understand some of the different dimensions of the scientific selves. I like this phrase by Dustin and Gallison in their book Objectivity, where they point out that their intention is so they were inspired by Foucault's idea of the technology of the self, but they tried to apply this to the history of science, and they said they paid attention to the practices that constitutes the subjectivity of the scientists and the scientific selves. It, my my attempt goes a little bit in the same direction, but um, with an emphasis on the social dimension. So it's not. It matters to me not the scientific selves, individual selves, but the scientific ourselves. How science is made by a subject that perceives itself as plural and indeed is plural. And I explored this through several case studies so far. One case study, I presented one case study some years ago, I think 2 or 3 years ago, in not this seminar series, but what was it? The Proteus seminar series. And it's now a publication is coming out, imaging a black hole shadow through the Event Horizon Telescope and Science in Context. Then another publication is dedicated to the multi-messenger astrophysics or astronomy. And this will be published on Centaurus, the journal of the History of Science journal of the European Society for History of Science. I'm working also on nuclear fusion research, and this is an ongoing collaborative project with other colleagues in the PNRR scheme. And then I want to come back to my 18th century and some problems in 18th century astronomy, and particularly I want to show how and why Uranus discovery was a shared discovery. Okay, and that's the background and the big picture in which I am, and in which what I in which it will be placed what I'm speaking about today. Um, there is a concept that I will use today, which is what I call epistemic constrained or and epistemically constrained collaboration. So collaboration that merges because of constraints of epistemic kind. Uh, Now, what is the standard account of science collaboration or collaboration in general? This is that collaboration is social in itself. It's normally understood as an efficient way to solve certain epistemic tasks. For example, to run a large experiment, to analyze a huge amount of data. You cannot do this alone practically, I mean, because there are too many data. A large experiment is too much complicated, and so on. So you need others. You need exchange of ideas because your mind is not powerful enough, or because you're not right enough to 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 run an experiment as a single person. So it's just division of labor. We could do alone in principle if we would be affluent, if we would be intelligent enough, if we would be powerful enough. But it's just more cost effective doing the same things that we could do under other not realized circumstances. What we it's just more cost effective doing together what we could do theoretically in principle also alone. Look, normally collaboration as a social constraint is viewed as something irreducible, while there are many sociologists, some sociologists of science, some philosophers of science, who could have a reductionist stance, who could call themselves reductionists. Collaboration is a social behavior that is completely irreducible. There are social constraints, but reductionists usually think that social constraints are irreducible. And my idea is that, well, there are non-trivial cases in which the main push toward collaboration, toward a distinct social behavior, is given not by social motivations, but by epistemic motivations and even obligations, constraints. So there are cases in which collaboration is required by the epistemic structure of the problem, which acts as a constraint to use resources by largely independent individuals. I mean, even the most powerful artificial intelligence could not do alone, could in some circumstances, because of the structure of the epistemic structure of the problem. And in this talk, I will contend that one of such cases is multi-messenger astrophysics or astronomy, as others say. In sum, if you think that multi-messenger astrophysics is strongly collaborative only because it's a big science, and big science must be collaborative because of the resources involved, then I believe you're probably mistaken. I suggest that multi-messenger astrophysics radically needs collaboration because of its epistemic structure. And this is my thesis. But first of all, what is multi-messenger astrophysics? Well, the concept of multi-messenger astrophysics or multi-messenger astronomy, there's also there's a little bit different emphasis, but there are many articles, papers that bear both of them in a closely way, in a quite undistinguishable way. Well, this concept traces back to the early 2000s. It's relatively new and gets viral only in 2010s, so 15 years ago. It consists in the combined study of radiation, which is conveyed by mediators of completely different nature, by neutrinos, by photons in all wavelengths from gamma rays until from gamma rays through visible light until radio waves, of course. Then there are gravitational waves and cosmic rays, which are charged particles or light atomic nuclei. Note that, as some commentators, some scientists says today, they are the mediator, or they can be understood as the mediator of the four fundamental interactions. The important turn is that they are not studies in themselves or um, in their reciprocal relations. Like if you are a theoretical physicist or a particle physicist, then you probably are interested in what kind of particle is emitted, what kind of features it has, the mechanisms of the emission, and so on. But if you are an astrophysicist, you're mostly interested in the sources and the mechanisms according to which a certain source can emit this or that radiation. And so in multi-messenger astrophysics, this radiation is used as a mean to explore frequently extragalactic sources, which are usually far away from the Earth. We also did some, particularly in collaboration with Eugenio Petrovich, some years ago, we did some bibliometric work in progress about the use of the phrase multi-messenger astrophysics and its the way in which in scientific bibliography are this expression is reported, and it's impressive what happened after 2017. That's we can skip this today. It's not so important. What is the key? The key point of multi-messenger astrophysics? Well, in standard astronomy, every object, every astronomical object is you can say it's a multi-messenger, is a multi-messenger source in the sense that even the sun can emits, of course, photons and many other um, visible photons and light also in other wavelength, but it also emits neutrinos. It also emits um, cosmic rays. And you can study their correlation. You see the sun, you know that the sun is the source, and you're curious about certain messengers that the sun may have sent out, and you want to study their correlation, so to understand the mechanisms behind uh, the correlation of multiple messengers. But in multi-messenger astrophysics, what you don't know is exactly the source. So your starting point is not the source. Your starting point is the coincident messengers that you can detect, that you detect actually. And by studying the correlation of these emissions, you reconstruct the source and many other features. So in standard astronomy, you start from the sun, you have models that say, for example, the sun will emit this and that, and if uh, emits this, then you expect that you will detect also another kind of emission under some circumstances. In multi-messenger astrophysics, we start from the emissions, and our models say, for example, this emission within such range of energies could correspond with this or that source or mechanism. So it's the approach is very different. Plus, multi-messenger astrophysics deals and try to give an answer to two problems. The first problem is, which may or may not be present, as what I would call the subthreshold event problem. Well, every instrument, every experiment has a threshold under which a certain event is not considered significant. It can be registered, it can be recorded and archived in our archives, but in itself, as a single messenger, so to speak, is not significant. But they could be significant. And imagine to have many insignificant, per se insignificant events. But you note a correlation between them. Then they are significant if combined with one another. If they are subthreshold events, single subthreshold events, but when combined, they are significant. So joining together two or more subthreshold events, coincident signals from different messengers can lead to the discovery of an important extragalactic, for example, source. Then we have another kind of problem that I call the epistemic separation problem. The messenger provide complementary information which is irreducible, right? Neutrinos are neutrinos, and they are not like gravitational waves or photons. And this kind of information can only be detected by experiments or instruments that are dedicated specific to that kind of messenger. You cannot have a neutrino detector, a neutrino telescope, for example, the ice cube in the southern pole, that also detects gamma ray bursts. That's just not possible. Are possible to mix up some of the messengers, but not in this way, or some different wavelength, but not in this way. So when applied to remote events, a single messenger investigation would usually result into just a partial and well, unsatisfied knowledge about a certain event. We have to combine more messengers, more than one kind of information to have to recognize the source. And so source detection strongly depends on our capability of answering these problems, which are crucial in multi-messenger astrophysics. But what is crucial, more crucial if you want, is the idea of theoretical models. These problems and multi-messenger astrophysics reveal an obvious technological counterpart. I mean, we have to develop sensible, dedicated instruments to detect this and that emission. We have to develop dedicated software. We have to develop statistics capable of coincidence searches and capable of distinguishing noise from the genuine signals, right? But first of all, we have to develop theoretical models to predict source-event emission relation to represent how a certain event could evolve into a kind of emission. Otherwise, every detection could potentially be insignificant. Why? Because we do not know. We have no information about the source in advance. But if you have good models of like a supernova emitting story, then we can start from the emission and try to reconstruct this story to understand that that source was, for example, a supernova. Well, at this point, I want to skip what what would be an important point, that is to try to present the idea of model. I think that every one of us has more or less good idea of what a model is. Uh, Incidentally, there has been and there is much research on the notion of models since the 1960s, more or less. And we have these two big classes of approach. There is a semantic approach to scientific theories, for which models are structures endowed with some kind of structure similarity or identity. That can be isomorphism or homomorphism with a target phenomenon, with a phenomenon in the reality. And then there is another more recent view, probably, and even more appealing today, or considered as more appealing today, according to which models are just fictions, like narratives, like stories, like novels, which employ fictional entities, more or less in the way novels employ characters to describe some kind or relation among characters to describe some kind of situation. So an important result is for this approach, and that is that models are not only descriptions of situations, but prescription to imagine something in and the development of something, the evolution of a story. To say at these conditions, this situation will evolve in this other situation. Well, I think that both models of model have their own merits, but I want not to explore this further. I just add also the idea of data models or models of data to this couple of concepts. What is a model of data? It's a model obtained by extrapolating from large sets of data and extrapolating correlations, and we expect that the same, more or less the same result with minor variations will also be the next output. Uh, this idea is particularly due to Supes and applied then to hacking and others to astronomy. Supes, I think he started or he had in mind mostly social sciences. Uh, I think that this is a good idea. His starting point was Tarski's logical concept of a model of a theory. Tarski thought that, or understood a model as an interpretation of a theory. He was a logician, so a theory for a logician or for Tarski was just a set of logical formulae. And what is a model? A model is just an interpretation of a theory, of the set of logical formulae in which all valid sentences are satisfied. So let us apply to clarify the idea also. Let us apply it, for example, to physics. You know, there are many models, for example, of quantum mechanics. And in quantum mechanics, there are also conflicting models. But every model is somehow, and to a certain point at least, coherent, consistent in itself, and is a possible realization of that theory. But so this what Supes called models of theory. But then the models of theory could also address us toward certain experiments and maybe allows for certain experiments, but other experiments are prohibited by the same model. And so models of theory give rise also to models of experiment. They are analogously the permissible experimental setups of a certain model within a certain theoretical context. And then every experiment give rise to data that are, well, if you repeat and repeat and repeat the experiment, you will find not exactly the same results, maybe, but you can find results that are not so much different. And so, after the level of the models of experiments, there is the level of the models of data, which are permissible realizations of the data made to fit a prepared experimental environment. The idea is that the models of a theory select certain models of experiment while prohibiting others, and certain models of experiment select certain models of data while prohibiting others. This is important because in this, as Supes said, models of data are designed to incorporate all the information encoded in an experiment, which can be used then in statistical tests of the adequacy of the theory. In other words, and very simply, models of data or the data from experiments serve to normalize and update models recursively through feedback action. Uh, if you find outliers, so statistically data that are statistically strange, or anomalies in your data, then well, they are suspect and call for revisions either of the model or of the experiment itself. And in this, you can have an idea of what the feedback effect may be. Since data models are prepared to fit a model of experiments, and this in turn and in turn, models of experiment are prepared to fit a model of a theory, then the output data can be used to predict expected results and to update your model, of course. And this is what happens in multi-messenger astrophysics. If the multi-messenger astronomer has enough data, then he or she can pass from the observed emissions to the source itself. So you can start from the observed data, which is the level of the models of data, and you reason that after all, the observed data are detectable by certain devices only, the level of the models of experiments, and they are possibly produced by certain sources, which is the level of the theoretical models. But in this kind of reasoning, our arrow goes on the other way around with respect to super nestification, so to speak. But this is exactly what has going on in what is going on in multi-messenger astrophysics. This is what I call the mother of all messengers, the detection, or no, the sighting of a supernova in 1987, the so-called supernova 1987A. It's noticeable because supernova are powerful, spectacular, very bright explosion of massive stars. And this was a supernova type second, core collapse supernova, a wonderful explosion. Unfortunately, it could be seen only in the southern hemisphere. The previous supernova recorded was Kepler's supernova in 1704. It's very rare. It's not rare in itself. I mean, supernovae happen many times in the universe, but what we can see is just a tiny portion of this. Well, people in 1987 were really lucky to observe this. In 1987, models said that a neutrino burst must have preceded the optical sighting. Of course, not every model, just some model of a theory. There was a theory of supernova, and some models said, okay, you will probably observe a strong neutrino burst just minutes or seconds before. Then a search for a neutrino flux was initiated in the archives. It was an archival search in the archives of three, I think, detectors: the Kamiokando in Japan, the Homestake in the US, and the Mont Blanc between France and Italy. Uh, and astronomers really found that there was a flux, there was a neutrino flux. Details were implemented in the models. Some models were just be excluded, and some other models were developed further and further. And now, with more precise models in hands, scientists, the astronomers, could also revert the cycle and pass from the neutrino burst detection to the source identification. So, let me call this the guiding function of multi-messenger astronomy models. This guiding function is of two kinds, I think. First of all, there is the level of inferences. Um, Models help us select phenomena based on the data we encounter. They guide our inferences. If one model is right, then other are excluded, and so on. Um, in other words, and to put it as I like this expression that of models like blueprints that Michela Massimi adopted in her books, in her recent books on models. Michela says that models open up windows on reality, on how reality will appear once a particular vantage point is adopted. And models can be tested, of course, to know if that vantage point brings us to some interesting result or not. But then models also guide our experimental setup or our experimental projects, our experimental design. They do not only include theoretical elements about what kind of mechanism is working, what kind of effect we will observe, or what kind of calculations will be produced or employed to understand a certain phenomena. No, models also allow uh, or involve operational instructions like this. If your instrument detect neutrinos energetic enough, that will be released from a galactic or an extragalactic source of this kind or another kind, then you have to quickly search for other emissions with other instruments and so on. If your instruments reveal a neutrino flux, then the model also says the neutrino flux will be followed up by other kind of emissions. And this is linked to our models of experiments. And so this idea has promoted the construction of infrastructures like the so-called alert networks like SNEWS, which is the alert network for supernovae, or AMON, which is an integrated alert network for multi-messenger astrophysics, or this GCNTAN for gamma rays and global position global network of gamma rays and other kind of informations. Now, if you look at the multi-messenger detections so far, they functions along these lines. They function in this way, according to the structure. One of the most important success of neutrino astronomy was in 2017, when LIGO Virgo detected the gravitational wave from a neutron star binary merger. Look, every signal and this image is associated with a certain possibility of location. Like the gravitational wave signal served to issue an alert. that informed the gamma ray burst astronomers to look with the Fermi telescope, which is a telescope located outer of the atmosphere. And the window of possibility was then reduced, strongly reduced. And then finally, and then they also provided information to the optical astronomers to point their instruments in this or that direction with all the technological constraints, of course. But they correctly identified what was the optical counterpart of the gravitational wave pulse. And so many single individual antennas or telescopes collaborated to one result. They also must do that. I mean, there was no possibility to identify the optical counterpart, the counterpart, or to know exactly from where the signal was emitted, if not, if this line of thought wasn't followed. But I think that after this double guiding function about inferences and about experiments, there is another important, maybe in this context at least more important, or more important to me, guiding function, which is the guiding function which is the idea that models also promote the scientist's choice about the social behavior. 1 month after that detection, in September 2017, the IceCube Neutrino Observatory at the South Pole detected a high-energy neutrino pulse and issued an alert. The alert was then accepted by the astronomical community, and the Swift X-ray telescope reported that they found some sources of X-rays coming from the same area of the sky. And then gamma rays were also found, and then optical sighting were also optical detections were also found, and the window narrowed and narrowed and narrowed until the astronomers understood that it was a blazar. Well, note that every passage involves different messengers that carry different information because of the epistemic separation, remember. And this messenger can only be observed by different instruments. There's no other way to do this. And the IceCube, and they must, particularly in the early phases, in the earliest phases, they must be coincident signals. Otherwise, we cannot locate, we cannot have any good information, and we cannot locate rightly the source. So this approach, the multi-messenger approach, implies that multiple actors, or multiple facilities, if you want, must share their individual contributions. They are individual, they are largely independent from one another, but they have to share information. They must accept to issue alerts and to send information out so that others can profit of this information and put forth a common effort. In other words, they have to collaborate. just because they are actors that cannot have complete information, because the information they may have is uh, just partial and comes out through messengers that are different by their very nature. So, just a recap now, and this is also my conclusion. A model provides indications about the observational strategy that should be adopted. It predicts which messengers are expected in the observations, and it also predicts the order in which they are expected. But note that for many technological and also theoretical reasons, it's not possible to build a single detector capable of observing the entire electromagnetic spectrum, and not to say all messengers. And most observations, as I said, especially in the earliest phases, must be made in nearly coincident times by distant stations. For example, gamma rays are mostly observed by space telescopes because the atmosphere filters out gamma rays for our luck. Hence, multi-messenger astrophysics needs multiple highly specialized separated stations. And yes, collaboration is of course a multifaceted, multifactored phenomenon. But in this case, in multi-messenger astrophysics, I think we have now good evidence enough to say that it is the epistemic structure of multi-messenger astrophysics, the use, in particular, the use of models in multi-messenger astrophysics that requires some level of collaborations. And so, assuming that the collaborative behavior is a social strategy to solve a certain epistemic problem, but it is a social strategy, that behavior, that social strategy, is selected not by other social components, but by the structure itself of the problem, which thus acts as an epistemic constraint. Thank you very much. I just have to say that I already had this this image was already included in my presentation on the EHT case 2 or 3 years ago in Prometheus seminars. But I think that I wanted to have included this today as a kind of linkage of this activity. So thank you very much.
Thank you very much, Luca. Well, I have first to say that it was very interesting. You touched so many topics, and you also, as you have shown us, the way in which you know the social and collective work is behind. The scene, you know, of our major achievements in multi-messenger astrophysics. I have actually a question as an historian of science, or at least from the perspective of an historian of science, in the sense that if we look at large collaborations in general, not just of course, in multi-messenger astrophysics, but think about big science, like the one that we do at CERN, or you know, when we have to handle large collaborations that you know, also involve different nations and different parties, stakeholders. funding, for example, by funding space missions that prepare, the ground for new collaborations. Well, in all these cases, we have different funding to be raised that are asked to people from different countries. Well, not only people, but stakeholders in different countries. We have representatives of the different um, parts of the collaboration of consortia. So we have those that are in charge of the theory part, those that are in charge of the experimental part, and they have to report to internal meetings. Normally, it takes years to prepare large collaboration, be it on multi-messenger astrophysics or in other fields. So, is this character that you highlighted of social collaboration something that is common? Of course, it's common to our way of doing big science today. But is there something special to multi-messenger astrophysics in your view?
All
If yes, what's really so special? Or if not, then we have perhaps to look at the economic structure of the way in which we do science, in our epoch.
Okay, yes. Col Multi-messenger astrophysics as a collaboration, as a collaborative effort, is really special because it's not like a clear collaborative project. It's not a one project. It's more. It's interesting because if you look at the production or the handbook production in multi-messenger astrophysics, so in, how to say, um, in presentations, in talks that present multi-messenger astrophysics, etc. It is presented both as a project, but a project of projects, and an approach. It's an approach in the sense that it's like, it's as I said, it's not a one program, one research project. There is nothing as this multi-messenger. No, there are many families of multi-messengers, messenger possibilities and collaborations. It's a collaborative, but it's more a cooperation of between different and many collaborations. So I must say that I learned since years now to distinguish among an informal and more philosophical way to speak to speaking of collaborations of of the idea itself of collaboration and a more institutional way. A collaboration is something that has that is established by some kind of agreements and so on. Whereas the idea of collaboration is more an idea, something conceptual. People that work together on certain things. So, in what I see the peculiarity of the multi-messenger approach. But certainly, multi-messenger approach is a collaborative approach. And what I want to stress is exactly this idea of a collaborative approach. Okay. Yes, there are, of course, many things many aspects that collaboration involves, many institutional aspects, many science diplomacy aspects that collaboration includes. Um, I do not think that every aspect that epistemic aspects prevail in general, but I wanted to stress that epistemic aspects are also important. and they are as important as many other aspects. What I don't like, what I completely dislike, is the tendency um, to reduce something to something other. So this reductionist temptation. I'm not a reductionist. I just wanted to stress that, of course, sometimes the social components cannot be reduced to others, and also epistemic components cannot be reduced. These components conspire to um, form the reality that we, as philosophers of science, as the historians of science, are interested in, I think.
Yes, thank you very much. I don't know whether Federico or Marco also have comments or questions.
Yeah, sure. Can you go?
Prego.
Okay. Thank you, Luca. That was very illuminating for me because this topic is not within my expertise. So I was trying to reconstruct the general structure of your argument to get a better grasp. So at the beginning of the talk, you said that it is not multi-messenger astrophysics requires collaboration, not because it's big science, you said, but because of the epistemic structure that characterize it, right? So I understood. Well, I inferred that the argument will be something on the lines, it is not some technological difficulty that will ground the fact that collaboration is necessary, but something about the epistemic structure of how multi-messenger astrophysics works. But in the end, it seemed to me that you instead used technological difficulties exactly to support your premise. So I just wanted to ask you if I understood correctly that the argument is
Well,
that these difficulties are somehow insuperable, then the epistemic structure is such that we need collaboration.
there are technological difficulties, but even if this difficulty could be overcome, we need collaboration at any rate. I mean, um, one difficulty is that we cannot construct an instrument capable of detecting both neutrinos and gravitational waves, for example. But this is not technological differences. These are theoretical differences. And this is dictated by our best theories. It's not just technology.
Okay.
And
So
the window, even the window between, just even this also involves the problem of detecting um, photons in every wavelength.
mhm,
We cannot see visible light and gamma rays, and plus, even if you could do something about that, you need coincident messages, right?
right.
And so
Okay, so the point is, even if you have the technology to
Right,
detect
right.
Sorry
two
if I
different.
interrupt you, but there is a physical constraint to that. So you
Yeah.
have the
And
radiation.
physics and physical constraints
You
have to
can
do.
look at the same object by exploding radiation, but of course you look at different wavelength and different you know, even characteristics, properties, of the very same region, for example, so you point your tools, your instruments that investigate at different wavelengths the same object in order to obtain the knowledge, or to cross-check also the data obtained before by
Yeah,
collaborations, because the problem is that sometimes you have, background noises, you can have systematic errors, you can have that that must be cross-checked, and you do that. But this is, I mean, in astrophysics, it works like this. I mean, if you want to study disk instability of dwarf novae, for example, so of cataclysmic variable stars and so on and so forth, you look at different, you look at the UV, you look at X-ray, you look at different um, um, lengths of radiation. So, and you gain information, you build up, a puzzle, you put together these pieces and see that there is actually a coincidence and that it's not.
yes. So one way to put this is the problem is that the system that you have to build is somehow a distributed system. Even if you have the most powerful instruments or astronomer machine or artificial intelligence in the world, it has to exchange information with other. This is structurally similar to the problem of the Event Horizon Telescope as I investigated it in the other article. And so as I regard both of them as the two faces or the both parts of both barrels of the gun, of the same gun.
I see. Okay, thank you. I wanted to push you on this to understand better where was the limit. Thank you.
Thank you. Thank you for your question.
Hello, so I do have a question. I'm sorry for my voice. I
Go ahead.
caught a cold. And, so at certain point you discuss, sorry, at certain point you discuss like a nested models of models, and for example, like the dependency over like data analysis or like data models for the detection of those data, then the data processing, so models that you use to process those data, and then you get observations, and then you up to like validation of a given theoretical models or hypothesis. How's that difference from other large experiments like LHC? Because they do have they like different agents at LHC, they do have to collaborate because different models, because different parts of the final validation procedure requires different data models, different coding systems, different acquiring data processes, and so on and so forth. So how would that be different than multi-messenger astronomy?
Okay, I have a very quick and very simple answer. I don't know. I completely don't know. I mean, it would be very interesting to compare this with the LHC and so on, but I really don't know. It can be that many from the same model of experiment, many other data models can emerge. The problem is, according to Supus, would be that if you have too many anomalies, you don't have any pattern, you don't recognize any pattern, then probably your model are somehow crazy or cannot be used at all. But as I said, unfortunately, I'm completely ignorant about the LHC. But if you have some information that or some add-on, then I would be very interested.
Not specifically, but I was generally curious because I did work a little bit on
Yeah, I know. I
models
didn't
in.
my interests are more in astrophysics, not
Fair,
very much in
fair.
astroparticle physics, if not specially applied to multi-messengers. And they are cases, not theoretical cases. They're very practical, experimental cases, and so on. So I know, as far as I know,
Totally fair. Sorry,
from
I was
your work.
curious if it was.
Sorry if I jump in again, but that's why I was referring to CERN before, because
Yeah,
they I mean there was a cross check between the result of Atlas and CMS. So they had the two collaborations had different instruments, different tools, exploring, I mean, they worked on different aspects. Of course, they both concurred to the same aim, to the same scope. Of course, it was, to detect the Higgs boson and so on, but not only, and the events during the running of LHC. I mean, the events were considered from the two collaborations independently, and then, of course, they had these meetings where they built up a cross-check, and
yeah.
involving
So
also theoreticians. So there is the theory division at CERN that works precisely. There are theorists, phenomenologists, and experimentalists that work together. There are engineers. There are so that's why I
yeah,
this.
this more or less what follows more or less the line of Gallison's account in that book and Logic. Well, that book on microphysics. So my impression is
But
that
then, sorry if I push you farther on this point, but then isn't that because it's a potential. It's not just I'm not just saying this in order to. It's a really important question because it seems to me that one could say, oh, but this is a sort of signature of the way in which big science works today. So. And this is something that philosophers of science working on modeling and so on should take into account because when we talk about social collaboration, so in a sense they are forced to collaborate in part because of the physics, as we said, for different reasons. And this holds both for the microscopic, let's say, or for the high energy regime, but also, of course, for the study of multi-messenger, or let's say astrophysical phenomena that require a multi-messenger approach. But it seems to me that it's more related to the divisional, so it's really related to social structures through which we organize scientific research
I would
afterwards.
say it's more related to epistemic cultures, to different cultures, and in this sense, to the social structure. I mean, it's not that the social structure and the epistemic ideas are not related to one another. That's the point to me. Okay. And once one admits that this, I do not see too many differences. Of course, the division of labor has enormous influence. But that division of labor can be co-caused by other factors. And they are most of the time epistemic factors. I mean, epistemic factors are also involved. As I said, I want not to be a reductionist. I do not see epistemic factors as irrelated to the social structures. Okay.
Oh, no, I don't say that. My reflection was more like, okay, but so even the way in which we built up our reflections or what models are in high energy physics or multi-messenger astrophysics and so on could be a social product.
Yeah, of course. They are
And
not only a social
therefore, it's
product.
a social product, just like the division of labor, in big collaborations and labs is, it's the way in which we do big science, and there are some patterns in the way in which we do big science that are recursive. They are common to different fields of physics research. I'm not reducing all to the division of labor,
No,
but
no. I mean,
very important to
it's of course it's that it seems to me that science is social. It's obvious that it's a social product. It's not only a social product, as every social product. There are social products that are just social products, maybe, I don't know. But certainly science is not only a social product. It's a social product that is caused also by our relation to the world. And it's a social product that it's also related to the constitution of our minds and so on, of our individual minds and our individual minds and their interrelations with other minds and so on. So it's, I mean, it's.
I don't know if
It-
Marco has one more question, but if not, I have another one.
No, please go ahead.
So very last point, at least from me. Okay, you made reference to Michela Massimi's perspectivalism and so on. But correct me if I'm wrong, I think that your view is similar to an attempt at defining an epistemic value, so collaborativeness, let's call it like this, or collective collaboration or social collaboration. Is it an epistemic value for you? So, like, can we attribute the stages of an epistemic value to this or not?
I don't know. Well, I used Michela's book on perspectivalism, of course. But I just used there are many other things in that book on which I do not have really an opinion. I mean, but this idea, I like this unique idea very much of that models serve also to model our inferences possibility. About epistemic values, what do you mean as value? You mean the story of epistemic values as are used now in the philosophy of science, like?
Yeah, but even in pragmatism, you have this type of reflections on epistemic values. You have epistemic values that guide
Okay, yes,
your
yes,
way.
yes.
So models
Yes, you can
mirror
you can
necessary.
treat this as epistemic values in this sense. Yes, I think so. But I do not have particular reflections to this. Maybe I should, but
Oh no, it was
I mean,
curiosity.
there is something moral because not moral in itself, in the sense that I think that the practices that in which we are and also shape what we are. Okay, and what we should do, can do, and so on. You can treat this as a value. I think I've been influenced by Foucault himself and by Gallison and Doston's books. So it's there is also a value talk in that in objectivity, for example, where they develop the idea of well, not values. What are they called? I don't remember exactly, fortunately. But there is a moral idea. So
there are different
science
ways in which you can talk about epistemic values,
Yeah.
epistemic virtues, epistemic. So there are different, of course, connotations in different authors about this. But my
there's more a value than an epistemic concept, abstract concept. You're right.
Okay, thank you. If there are no other comments, questions, then we thank our speaker again. Thank you very much, Luca.
Thank you very much
Thank you.
for being
Thank you.
here.
See you.